So first, I'm just going to run through just quickly what the motivation is for doing this, then run through the proposed architecture, and then finally, we offload all this type of stuff. So I'm just going to have a quick couple of words on just how to offload this and lessons we've learned from offloading this in real production environments. So firstly, first part of the motivation. So Ben spoke earlier about the sort of mega flow caching, which is how it really works in the kernel today. Previously, there was, from the history that I understand, and there's a lot of people in this room who know this a lot better than I do, there was a microflow cache above the megaflow cache. This still exists within the eBPF NetDev implementation, which is the Userspace implementation. However, for the reasons that like Thomas spoke about earlier, that Ben mentioned, this isn't currently in the kernel. So all I thought about was, hey, is there an easy way we could just quickly hack this up with XDP and have something we can try and have something we can see whether this actually gives us some interesting performance benefits. And then suddenly we're actually able to use this within the kernel. So this presentation is really just going to give a really quick, small example. This is not, again, as I said, not earth-shattering, not that new either. So why the kernel? We've seen this now. There's, if you're outside the kernel gives you a lot more maintainability because large-scale data center operators tend to worry about two things, performance and maintainability. I actually had a conversation recently at a conference with somebody from a very large hyperscale data center who they'd implemented a small amount of function as a sort of patch within the kernel. And they've now got a team of 50 engineers maintaining this small patch because they have to keep it up to date as the kernel changes, as things change, and as things move around. So for these types of guys, being able to stay fully compatible and fully with the kernel gives them a huge advantage. So that's really what the motivation is for doing this type of thing in the kernel. Now, what TC and XTP-based eBPF give us is suddenly we have this ability to add these small programs into the kernel, to add this type of data plane development, which we haven't been able to do before. As Thomas said, it's the fastest thing he's been able to develop and move these things into the kernel that he's seen so far. It gives us a huge amount of flexibility, and it gives us a great compromise between maintainability and performance. Previous work on this little space, eBPF, as you've seen, it's a fairly hot topic at the moment. My colleague Simon Horman spoke about actually having a eBPF TC-based pre-classifier last year at this conference. All I'm doing is pushing this down into XDP. There's also obviously everything Thomas is speaking about, and Will, who's speaking next, has been exploring eBPF-based OVS. So lots of fun things going on, and lots of things which I've really based my work on. So all I'm doing is a very small step. XDP, Thomas again spoke about most of this earlier, just to prop in the current use cases. And one of the key features, so something Ben mentioned earlier is about the packet overhead. And that's something which XDP has tried to address. So this is before you actually get your SKB attached to the packet within the kernel. So your SKB is the metadata within the kernel, which handles a lot of the processing. It gets used within TC, it gets used within NetFilter. And so all we're doing is we're actually processing the packet with XDP before we attach all this metadata. So we actually have less overhead and we have less other things going on beforehand. We have some very simple actions, so all really we can do is drop or pass. That means in the future, and this isn't something I'm going to speak about a lot here, but there's potential here for improving things like sort of OVS's DDoS protection, DDoS handling, because this is actually one of the use cases that XDP is already being used for today. This is actually Dave Miller's feature of the year. I'd encourage you all to go and check out his keynote from NetDev a few weeks ago. And there's just a quick link. If you click on it, there's a lot of information about XDP. I've tried to collate all the different slide decks and bits of information I could find out there. So there's lots of info there. It's just a link. It's on our OpenNFP website, which is just a little website we have with a bunch of open source stuff on. So I'd encourage you to click on the link and check it out. Right, to get to the actual architecture. So the key difference, the key issue we have here is the fact that XDP has very, very limited metadata at the moment. All it has is where the packet starts, where the packet ends. That's all you have. So to actually use this, we will need to add something in there. We will need to have a mark field. So what I've done here is I've taken the concept, which is the SKB mark, and I've just put it into XDP. So we have a small mark field, which will just be able to give us enough information to understand what actions are needed on that particular flow. You'll also notice I have, as Thomas was explaining about the BPF maps, I have two maps here. One of the things that Ben mentioned earlier was the key problem you have if you have an exact match cache is how do you clear it, how do you keep it up to date, and how do you make sure you don't have a huge amount of dead flows in there. I'll speak about this in a second, but the way it's currently done within the Userspace OVS implementation, at least from my reading of the code, which may be incorrect, I'm very happy to be corrected. All that happens is effectively as flows get marked as dead, they get cleared out by the slow sweep of the EMC. That's how that's getting cleared, and that's how that's getting moved through. Now, using this cache clear map, I'll talk a little bit more about this later, this gives us a little bit more flexibility to clear things out, move things in, but we'll get there. And also a classification map, that purely involves, that's just got the hashes and the pointer to the flow, actually the flow entry. The yellow things are the things which will need some modifications, so we need a pre-classifier to actually handle the SKB mark pre-classification. We'd need some form of map interface within vSwitchD, and also we need to add the mark field to XDP, so there's a little bit of change there. So those are the three changes that would have to happen in upstream code. So the eBPF program would be very simple. Two maps, one containing the pointers to the flow structures, the other one just notes the amount of hits for each entry in a period of time. Now that period of time is not something I have actually defined yet. This needs some work, but it's purely just to say, look, we can monitor how many times flows are getting hit so that we can actually use that as a mechanism to clear the flows. And if the two hash tables match up, that means that actually clearing an entry within the one when you're checking an entry in the other is very easy because you don't need to do any more measurements and so on. You know which entry it is, you just clear the same entry in the other table. So the current proposal would just be a single exact match hash, and this could obviously be extended in the future. We could add some wildcarding in here. It just depends where the community would want to take this. If this is something people find interesting, we can take that type of thing further, and we can discuss it in much more detail. That's pretty much on the OVS program. And the kernel infrastructure, as I said, XKB mark field, XDP mark field would be needed for metadata. And this can also then be used for things like net filters. So this would not be an OVS-specific feature. We could use this for net filter classification. So this could actually build in pre-classifiers into other bits of the kernel sort of data path structures. We need to really just decide what the benefits are of doing this. So Brendan Blanco had a really good presentation at OpenStack recently. I'd encourage you all to go and check it out, where he spoke about some of the potential future use cases. vSwitches came up as one of the use cases for XDP, as did vRouters and numerous other things. So if we want to actually do that type of thing, we would need to start thinking about putting this type of mark field in, but this is a discussion to be had. And it may be that actually the benefits of doing this within XDP are not big enough. This is something which I'm hopefully going to get to test out over the holidays. It could be very possible that we try this out, and this actually, the benefits we're getting over TC eBPF aren't very large. Now, there's been clear examples of that the benefits are pretty big for things like the DOS use case. So what we have with the DOS use case is we get about 20 million packets per second, which we can touch and drop for XDP, and around 5 is what we saw for when we do touch and drop with TC eBPF. But obviously, that's a very specialized use case, and that involves then not actually adding in all the SKB data. And there's lots of things which mean that that's the ideal use case right now. So actually, we're going to have to test this and see whether it actually works. So I'm not saying it works yet. This is something we could do. Again, the user space architecture, what we're going to need. So part of the aim which I had was to try and keep everything as similar as possible to deep-if NetDev, because it's just nicer if everything looks quite similar. So what I've tried is, basically using the same key value storage you have with a EMC entry, initialized in the same way as you would initialize the EMC cache. So basically, you use those same types of functions. Obviously, it's a little bit different when we're initializing the maps and using the maps, but try and do it in a similar way. And yeah, as I said, we need a map for the actual, that shouldn't say XDP prog. That should say the flow structures. And then we need a map as well for the removal of the dormant entries. Now, the dormant entries, that's basically when we're trying to look for things which are dead. So at the moment, as I said, flows are only removed if the flow dead sort of flag is actually set. However, what we're going to have to do is we're going to have this slow sweep run through and check. We're going to have some rules there which say if there's been this many hits or no hits, we will clear this flow. And that depends on the actual timings we have, how long we have, in terms of how long it takes to run through the cache and so on. This needs a lot of fleshing out. This is not complete. This is just the first proposal. This will give us a lot more advantages through the exact match cache. Now, obviously, there's a lot of things you miss out on with an exact match cache. Because of the way the wildcard table works, that means that the user space doesn't actually see a lot of the flows. So a lot of the flows never actually get to user space. So this would never be able to contain all the flows. So if you have a bunch of flows that would actually hit the same mega flow, you're only going to get one of them cached. That's just the way it is right now. Maybe in the future I can think of ways to kind of get around that, but for now that's the way it is, and that's, I think, also the way, as I understand it from my very basic reading of the code, the way the EMC works right now. Maybe we could add a bit more in there, but for now that's all I see happening. So now I get to the final part of my presentation, which is running pretty short here, but that's hopefully okay, is how we would link this into offload, because obviously what we do is offload things, and something we always think about is how can we improve the performance of this and how can we fit it into the way that we do things. So really what we do is we have a low power, fully programmable 72-core smart NIC. You've got 576 cooperative multiplex threads on there. That basically means each one of these small processors has 8 threads running. And as one goes off to go and check a piece of memory or check something out, another one can run, and so you never end up actually with dead cycles. So all your cycles get used. This is part of the way we are able to be very efficient and get very high performance. So what we have right now is we have eBPF offload, which we've upstreamed. So we've actually had it go in this week for XTP, and we had it go in a couple of months ago for TC. So that means if you write your eBPF TC or eBPF XTP programs, we can transparently offload those. The maps is still something which we're working on, but we'll get there hopefully in the next couple of months. So we're looking to get there pretty fast. So that gives us fully transparent eBPF offload. So you can suddenly run these programs in fairly performant manner in hardware. I'd encourage you to check out the presentation me and my colleague Jakob, who's the real brains behind this, did at NetDev a few weeks ago. That explains in more details how we're doing it right now, what the problems are, what the solutions are, and where the things are we're going to have to work on as a community far into the future. So I'd encourage you to go and check that out if you get a chance. The second approach we have is OVS kernel Datapath offload. Now, this is actually where I got the inspiration sort of to try this flow cache thing. I then went and tried it and realized that all this stuff existed, all this infrastructure, a lot of it had been used in lots of different places. But that's actually where I got the first push from personally. Because we found, and this is in real production use cases, we found a real advantage from having that exact match cache at the front of our firmware data path. And that's given us a big performance boost. And this is in real life, real use cases. So that's kind of why I thought actually this could be something interesting to add. There are a lot of problems, as Ben mentioned earlier, as a lot of people have spoken about in the past. You can just go and check the mailing lists. But I think this is something where in real production use cases, we do get some very nice performance improvements. So that's why we basically went down this path. There's a lot of other stuff there. We offload contract, and we basically add in these hooks in the kernel today. Where those hooks exactly sit, we don't really mind, but currently that's our implementation. And we get some nice performance of that. 6 times reduction in your TCO in terms of servers used and so on. You can go check out the links if you guys are interested in following that. And some interesting performance benefits with contract as well. This is just the model of our eBPF acceleration to give you an idea of how it works and how you can do this transparent offload. So what we have is, so as Thomas spoke earlier about the verifier, so we've made some changes to the verifier recently, and this is all upstream. So everything on this slide is already upstream. Nothing here needs to still go. This is all there already today. So we've made a couple of small changes to the verifier, which means you can reuse the infrastructure. So if anybody else ever in the future Mellanox or Intel or anybody else wants to also do an eBPF offload to a NIC, we have that infrastructure there, which is now being built in a way that is reusable. So anybody can reuse that infrastructure in their own NFP in our case, but own hardware JITs. So all we do is we take the, what we have is we've created an offload object, which contains the bytecode, and all we do is we translate the eBPF bytecode into NFP assembler. So it's just a straight mapping at a very low level. There's potential in the future where we could optimize things like LLVM so that we produce the eBPF bytecode, so it's optimized for the NFP target, the same way you would optimize it for an ARM target or an x86 target or anything like that. But this is all future work, and this is things we're working on. We're also working on, at the moment, I'm building a little bit of code for the Verifier to do some register liveness analysis in there, so we can improve the performance we get there. And that's really how it works in terms of, this is just a visualization, excuse me, this has got a bit fuzzy on the resolution here, but this is just a visualization of how other Datapath works. The key thing to check out is the exact match flow tracker, as it's been called there at the front of the whole Datapath. That's the thing where we're getting a lot of improvement in performance benefits. And that's kind of the similar thing which I'm pushing here for XTP. And yep, just a summary, as you know, XTP does have some potential as a preclassifier. Needs a couple of changes, but there's some potential there. We could use it. I'm very happy to have that debate with anybody who's keen to have it. And really, for me, the response is here. I'm just looking to see what the response is. If people are interested in this, then this is something I can drive forward and do a little bit of work on. Nothing as interesting as the work Will is doing, obviously taking eBPF and basically using it to build the whole OVS. And there's lots of other people doing lots of great work. But that's really what I've got here, and I'll leave it there and say thank you very much.